In this video, we are going to see about the DC characteristics of an op-amp. That is, we are going to see what are the parameters that is going to affect the output voltage of an op-amp when a DC input signal is given. So let us see one by one. For an op-amp, the input can be either a DC signal or an AC signal. If it is an ideal op-amp, the op-amp responds equally to both the input signals. Whether it is DC or AC, it responds equally. And it is also, the output will also be independent of temperature. So whenever there is a temperature variation, in case of ideal op-amp, the response remains the same. But practically, it is not same. In case of a practical op-amp, the op-amp response is not same with both the DC and AC signal because of two reasons. One is the temperature, the other one is the frequency. If you take the frequency, in case of a DC current, there is no frequency, frequency is 0. So the op-amp response is different. In case of a AC, if it has a low frequency signal, the op-amp responds well, whereas when the input frequency is high, the op-amp cannot respond quickly because of the internal capacitance present in the op-amp. So due to that, the op-amp will not respond quickly to the high frequency signal. So now let us see how an op-amp responds to the DC input. And in the next video, we will see how an op-amp responds to the AC signal. So there are various factors that affect the DC output voltage of an op-amp. The first one is the input bias current, input offset current, input offset voltage, total offset voltage, and thermal drift. So let us see one by one. If you take the first case, input bias current, we know an ideal op-amp does not draw any current. It means that this I1 equal to 0 and I2 is also equal to 0. So op-amp does not draw any current from the input. But practically, op-amp will draw some current for its operation. So which is represented by IB minus and IB plus. So this current IB minus and IB plus is called the bias current or input bias current, which is required to bias the input transistor. If you see the internal structure of this op-amp or internal circuit of the op-amp, we know there are two inputs in an op-amp. One is the inverting input and non-inverting input. You can see these here, inverting input and non-inverting input, two transistors are there, or you can find many transistors. So these transistors need to be biased. So it draws some current. So that is called the bias current. But here the problem is that practically no two transistors can be similar. There will be a slight mismatch. Because of that, the bias current may not be equal. So these two currents may not be equal at all times. Since these two currents are not equal, normally even the manufacturer doesn't know what will be the or which current will be higher, this current or this current. So normally what is done is, in data sheet you can find average of these two currents. Average means you're adding these two current divided by 2. You will get one average value, bias current. So if you see in the data sheet, you can see only one value. Two values will not be there. Only one value will be given, which is the average of these two currents, called the bias current. You can see here at 25 degrees C, the maximum bias current is 500 nanoamps. So only one value will be specified by the manufacturer for input bias current. Now, here you can see in this circuit, the input voltage is 0. That is, the inverting input is also connected to ground. The non-inverting input is also connected to ground. So, when input voltage is 0, the output should be 0 in case of an ideal op amp. But this voltage may not be 0 because here the op amp is drawing some current. Okay. So, let us see, write the nodal equation and find what is the output voltage you are getting because of this current, bias current, input bias current, and how to compensate this bias current. So let us write the nodal equation. First you see here this pin is connected to ground, that is the node B is connected to ground. So node A will be at virtually ground potential. This is VA is 0. So now let us write the nodal equation at this node A. VA minus 0 by R1 plus VA minus V0 by RF plus IB minus is equal to 0. Nodal equation means you are writing the sum of the currents entering this particular node as 0. Okay. So now we know VA is equal to 0 because VB is 0. So VA should be equal to 0. You can simplify this one. You will get the equation as V0 is equal to IB minus into RF. That is, IB minus is the current entering the negative terminal into feedback resistance RF. So this is the output voltage you get even when the input is 0. So what is this RF usually? It will be a very high value. Let us say it is 1 megohm. When it is 1 megohm, we have already seen that IB, this bias current is around 500 nanoamps. We have seen in the data sheet. So what you will get if you multiply these two, you will get around 500 millivolt. If I use this op amp with sensors which already gives the voltage in millivolt, this 500 millivolt will create a lot of error in my circuit. So this is a huge value which is not acceptable. Okay. So millivolt, though it is in millivolt, 500 millivolt is not an acceptable value. Somehow I have to compensate this voltage and bring it to 0. So I have to find a way for that. So what can I do? I can connect a compensation resistor in this point so that because a current is flowing, this current into this resistor will create a drop. Because of that, this potential will change, which will compensate or nullify the output voltage and make V naught equal to 0. So my aim is to bring output voltage to 0 by connecting a resistor in this position. So if I connect a resistor or compensation here, the circuit becomes like this. So or compensation here. So this current, you can see this current is flowing here, will cause a voltage drop here, and this voltage drop has to produce a negative effect here such that the output voltage becomes 0. Now I have to find what should be the value of this or compensation so that the output voltage becomes 0. Now this at VB, the potential is, this current is flowing here. So IB plus into R compensation. So if VB is this one, VA will also be the same thing. Because that is the golden rule of op amp. Second golden rule. Okay. Now again we will write the same nodal equation. But instead of VA will be equal to this value. So let us substitute this one for VA. Simplify it and substitute it. Now let us multiply this equation because I have a RF here. I am multiplying this equation by RF. And let me see here, IB plus and IB minus is there. That is equal to IB. So let us mark these two as equal, and with this assumption, let us simplify it. So now what is my objective? I want to make the output voltage 0. So if this should be 0, this component of R must be equal to this component of R so that this voltage will become 0. So this component is equal to RF. So now let us simplify this one. We will get R compensation as R1 parallel RF. R1 is the input resistance and RF is the feedback resistance. So this compensation resistor value is the parallel combination of these two resistor values. So by doing this, we can make the output voltage to become 0. That is, we are compensating the voltage we are getting due to the bias current. Next, we will see about offset current. So we have seen that the bias currents are not equal. So the difference between the bias current is called the offset current. Why there is a modulus here means we don't know which is greater. So anything can be greater. So it is normally represented like this. Now due to this offset current, there will be a voltage drop. So V0 is equal to IOS, that is the offset current into feedback resistance, RF. Now, if I reduce, we have seen that RF is a large value, it will be in mega ohm. But if I reduce this RF, I can reduce the output voltage due to offset current. So the effect of this offset current can be minimized by reducing the feedback resistance. So we know the gain is directly proportional to feedback resistance by input resistance. If I reduce this RF, what happens? This R1 is the input impedance, which is also usually a large value. If I reduce this one, the gain will reduce. So to have a reasonable gain, I have to find a method or choose the RF value such that I get a reasonable gain. So the best method is going for a T feedback. So you can see here, this is a T network. So this T network helps to reduce the feedback resistance, whereas you can also compensate this output voltage due to the offset current. So if you see, if you convert this T to this pi conversion, you can find what is the value of RF. So RF is given by this value or this equation RT square. You can see here RT is here and this is the RS part. So this one. So initially you have to choose RT such that it is very less than RF by 2. So with this assumption we can design the circuit. So by this way we can able to reduce the voltage due to the offset current. Next we have the input offset voltage. Input offset voltage is nothing but when both the input terminals are 0, output should be 0, but output may not be 0. So you are giving some voltage here or adjusting the terminals such that you are getting output voltage as 0. Okay. So in this case, you can see that the input voltage is 0 and the output voltage is given by 1 plus RF by R1 into the voltage here, that is the offset voltage VOS. So next is the total output offset voltage. So far we have seen two reasons for the output voltage when the input is 0. So one is due to the input offset voltage, another one is the input bias current. So these offset voltage can be compensated. In op amp, you can find the first pin and fifth pin as offset voltage. So you can compensate or you can nullify this output voltage by putting or connecting a resistor across these terminals and adjusting it to bring the output voltage to 0. So in case if you are not using any compensation like a bias current compensation, that resistor is not used, your output voltage total output offset voltage will be equal to 1 plus Rf by R1 into BOS plus Rf into bias current. In case if we have compensated this bias current, it becomes an offset current here. Okay. So next is the thermal drift. So this also plays a major role in changing the output of the op-amp due to temperature. Thermal means we know it is the temperature. So drift means change. So the output voltage changes with respect to temperature is called the thermal drift. So an op-amp designed for 25 degree Celsius or 20 degree will not respond the same when the temperature increases to 45 or 65. So this is called the temperature drift. You can see the data sheet here. Most of the parameters which you have seen, offset voltage, offset current, bias current, input resistance, everything is specified for this 25 degrees. The tested condition is only 25 degrees Celsius. So if the temperature changes, there will be a change in these parameters. So because already it is in millivolt and due to the temperature change, it may change. So the gradual change in the op-amp's parameter due to variation in temperature is called the thermal drift. So what are the parameters that can change? First thing, gain can change. Then bias current, offset voltage, all these can vary with respect to temperature. So normally these things will be expressed in terms of nanoamps per degree Celsius or millivolt per degree Celsius. So it will be expressed with respect to temperature. So the points to remember in this video is that we have seen about the DC characteristics or the factors that affect the DC output voltage of an op-amp. Input bias current, so that is responsible for biasing the input transistors. Input offset current, which is nothing but the difference between the input bias currents. Input offset voltage, and you have total offset voltage which is due to the bias current and this input offset voltage. Offset voltage means even though the input is 0, some output will be there. Next one is the thermal drift. Thermal drift means change in the op-amp parameter due to the change in temperature. If you like the video, do subscribe to Read Electric Vehicle channel and share it with your friends. Thank you.